All right, this is lecture 13, and today we'll be going over transference principles, or also known as sampling principles. These will be used, well, we'll see how these are useful later on, but sort of to recap what it is we're trying to do and why we're interested in these sampling principles. So we had introduced this quadratic form that was the sum of squares, and we were using it to count integer points on a sphere of radius square lambda, right? And we saw before, using the circle method, how to count a given asymptotic number of solutions as lambda goes to infinity as soon as we have 5 or more variables. That is, d is greater than or equal to 5, right here. Okay. In particular, the asymptotics gave that it's positive, and it grows at a certain rate as soon as lambda is sufficiently large. But we had that in 4 more dimensions. Every integer lambda has a positive number of points on the sphere. And that's not true in fewer variables, but as soon as you have 5 or more variables, you have a very nice regularity property in terms of how this asymptotic grows. So we can use that to define the spherical averages, which are just you introduce a probability measure on the sphere of radius root lambda, and this is actually on the integer points. So it's a sum of delta functions, one for each point, one for each integer point on the sphere, and then you normalize by just dividing by the number of points on the sphere. And of course, this is a probability measure, and it acts on functions that go from ZD to the complex numbers by just convolution. And you form your maximal function at every point by taking just the biggest average and absolute value. Okay, we've been doing this for a while lately, so I'm not going to dwell on it. And the main theorem we want to prove is that as soon as you have 5 or more variables, this maximal function, studied first by Magyar, then Magyar, Stein, Wainger, and then subsequently by Ionescu, is bounded on LP as soon as P is sufficiently large. And what sufficiently large means here, it depends on the dimension. So it's always greater than the dimension over the dimension minus 2, which is some exponent less than L2. Right, d over d minus 2 is less than 2 when d is 5 or more. And not only is that useful for the fact that we've already seen this theorem fails for p less than or equal to d over d minus 2 and for d less than or equal to 4 in any p, but it's very useful for us because you have little L2 is, well, since d over d minus 2 is less than 2, you have that this theorem is true on L2, and what we're going to do is prove the theorem on L2 and have some extra slack there that allows us to get to p smaller than L2. Right, so we saw last time that as soon as we had, say, d was equal to 8, that the dyadic maximal function, that is where the supremum is just over a set of lambda, say, between big lambda and twice big lambda, that these maximal functions had a uniform bound in 8 or more variables, where that bound did not depend on this big lambda here. That's not as strong as saying this is bounded on L2, but it is a step towards that. And we were able to get a logarithmic type bound when we had 6 or more variables. And we weren't able to say anything about 4 or 5 variables. The theorem fails for 4 variables, as we said already. Though you can recover it with a log loss, the dyadic maximal function being bounded, that is. And for 5 more variables, you get the dyadic maximal function is bounded on L2. And that's in part because the full maximal function is bounded on L2. And that's the latter being a stronger statement. So just recall some notation because I'll be using it throughout. We have these characters, either minus 2 pi I z, where z is a real number and integer, r mod z, z mod q, and so on, as we've been using throughout the course. But we use those characters to define various Fourier transforms. On RD, you just integrate a measure against it. And then on ZD, you do the same, but integration turns to summation, of course, because I'm thinking of ZD with a counting measure on it. So integration is summation here. And on the torus, on the d-dimensional torus, is defined just like it is for the real place for RD, but your integration is restricted to being over the torus. And that makes sense because the character has some wraparound. It's periodic mod 1, right? Oh, there should have been an F here. Let me draw that a little better. So inside of here, it should have had f of x, where f is a periodic function, one periodic function, and so that is well defined. Great. So one of the key steps in the Magyar Stein-Wainger theorem is going to be an approximation formula for this surface measure, right? So the surface measure was just the indicator function on the set of integer points, normalized by the number of integer points on your sphere. And when you take the Fourier transform, that turns into this exponential sum right here in the middle. And well, in the course of the proof, we'll actually work without the normalized one. And we saw before that there's the circle method. We use as a form of the delta method to actually start analyzing this sort of expression. When c was equal to 0, we did this in the first few lectures doing the Hardy-Littlewood theorem. All right. So some more notation. This is just to define the, just to state the approximation formula precisely. I'll write ZQ sometimes for Z mod QZ. I'll also write it as Z mod Q. And then we have these Gauss sums, which have linear twists in them, defined right here in the middle. And we pick some smooth bump function psi. It's going to be 1 on a very small box near the origin, not very small, but small. And it's supported in a small box as well, but a little bit bigger, so that we're fully contained inside of a fundamental domain for the torus, right? So remember that minus 1/2 to 1/2 to the d is a fundamental domain for RD mod ZD. Okay, or it's actually the closure of 1. I suppose we could just do that as the fundamental domain. Great. So our approximation formula reads as follows. This Fourier transform of this indicator function, well, it grows like lambda to the d over 2 minus 1. And then it's times something that is resembling the singular series that arises in the circle method in our analysis in the first few lectures. In particular, we have those Gauss sums that were just defined above. They're localized by this this function psi, which remember was supported in, say, minus 1/4 to 1/4 in all dimensions. And therefore, when I multiply by q here and subtract off m, that's saying that, so psi of q, c minus m, is supported in the box from minus 1/4q up to 4q to the d plus m over q. So around each of these rationals with denominator q, this localizing function is picking out a small neighborhood around it. Well, not necessarily small, it's a reasonable size, but it depends very much. It's as big as the modulus, or sorry, its width is inversely proportional to the modulus. Okay, and it's 1 on, say, minus 1/8q up to 1/8q in each direction, in each of the standard directions. Now this last piece here was the continuous Fourier transform, so the RD Fourier transform of the spherical measure on a sphere of radius square root lambda that we saw in the middle lectures, in the lectures 6 through 10 or so. And it's also shifted by a rational m over q again. And this is all up to some error term, which is where all of the approximations are being thrown into, all those remainder terms for the approximations that we need to bound and take care of. All of those satisfy a nice bound for the dyadic maximal function. It has some extra decay. It's noticeably a lot smaller than lambda to the d over 2 minus 1. So what I'm saying here is this is a lot smaller than lambda to the d over 2 minus 1, in the sense that it is, minus some exponent delta that depends on the dimension. So when you normalize by this factor, this is going to grow like lambda to the minus delta over a geometric series or a geometric sequence that we can sum up, which is great. But we haven't gotten to proving this yet. We're going to go into some sampling stuff for today. And this is also known as transference. So Magyar, Stein, and Wainger, building on work of Bourgain, which built on work of Polya Plancherel, Nyquist, Shannon, and so on and so forth, proved a very nice transference principle, which allows us to take Fourier multipliers on ZD that correspond to some modulus Q and to transfer them to operators that are on RD. So Fourier multipliers on RD. And actually you can do a whole lot more. You can do so by looking at linear spaces of Banach space valued operators. So that's a bit of a mouthful. This right here, this L of B1 and B2. B1 and B2 are finite dimensional Banach spaces. So for us, a very important example that we'll really use is L infinity of n, where brackets of n is just the set of integers from 1 to n, including 1 and n. And so this L is the linear maps between a Banach space B1 to another, a finite dimensional Banach space B1 to another finite dimensional Banach space B2. Okay, for us, that'll largely be RD and L infinity of n. And this restriction to finite dimensional Banach spaces isn't really a big one for us. Instead, what we'll be able to do is by standard monotone convergence arguments, we'll actually be able to replace this L infinity of n with L infinity of the positive real numbers or the natural numbers. But we'll still have RD because that's where our functions will initially live. Great. Okay, so that's what this L of B1, B2 is supposed to mean. What do I mean by having a multiplier? So I have some function mu that is initially defined on this. Oh, I think I want actually to write 1 over 4q. And it takes, at each value, it takes a linear map. Okay, at each point inside this little box, these little boxes were drawn above. Remember, got a little box 1 over 4q in each direction of width 1 over 2q. And you can extend this periodically by summing over all the different residue classes mod q. Okay, this gives you an operator defined on the torus that depends on q, of course, and I'll keep track of that dependence for the moment. And it's just given as Fourier multiplication. What they showed is that they showed this inequality, which is the transference principle. So they proved a bound that allows you to go from little LP, where I take values from, it's going to take values inside of the Banach space B1 and map those to little LP of a Banach space B2, or taking values in a Banach space B2. And that's bounded by doing the same thing, but on LP, the big LP spaces, where I have some other operator, TR of D, okay? Which is defined in relation to this one. And I'm not going to be precise about it today because we're not going, well, we'll get into what that means today, later on, actually. But what it means precisely for the spherical maximal function, we'll record when we need to. Okay. The important thing and what they do is they get a bound that doesn't depend on the dimension of the Banach spaces, which is why we can take little L infinity of brackets n to be little L infinity of the natural numbers or the positive real numbers. By monotone convergence, you need to have that uniformity in the dimensions. And it also doesn't depend on the big exponents p or q. Oh, yeah, or sorry, the big exponent p or the modulus q. Great. So I recorded for a moment how we're going to use it. Just to reiterate, we will take the Banach spaces to be these little L infinity spaces because we're going to have a maximal function. The maximal function for the the spherical maximum function, remember, is defined as the sup over lambda in n of a lambda f at each point x. And so we're actually going to say this is less than or equal to the limit as n goes to infinity of the sup over lambda in n of a lambda f. It's actually equal to it. And it's this little L infinity right here that we're looking at, that we will apply their transference principle. But let's go back and let's actually see where this came from. Their version, so in the Magyar Stein Wainger paper, which is titled Discrete Analogs and Harmonic Analysis, Spherical Averages. I'll write that down since I haven't yet. Magyar, Stein, Wainger. This is one of the seminal papers in the field. Discrete analogs and harmonic analysis. Colon, spherical averages. Okay, so that's the paper. In there, they give a very elegant abstraction. This lemma right here is a very elegant abstraction of a lot of work that happened over the intervening 80 or 90 years, whenever Plantarel Polya's theorem came out, and all the other sampling machinery. It's very slick and nice, but I'd like to sort of, rather than just go through their proof, I'd rather kind of build up to it and give an indication of where these ideas come from today. So one of the very motivating examples is the Shannon-Nyquist, or Nyquist Shannon, maybe it's more accurate, sampling theorem. And so this is the following reconstruction formula. If my function f has Fourier support, which means it's Fourier transform, and it says it's real Fourier transform, it's supported in the interval from -1/2 to 1/2, then at each point x, at each point x inside of the real numbers, we have the following representation for f of x. It's actually interpolated by the values of the function at the integers, which is a surprisingly crazy thing if you sort of think of just a general function and just kind of wildly going in and out, and maybe it's some sort of Brownian motion. This doesn't happen at all, right? However, when you have this Fourier support condition, you have a very strong restriction now on your functions. So I say this happens at each point x, and in particular, if you look on the right-hand side, it sort of looks like a continuous function, or you might expect it to be somewhat continuous, because these parts right here are continuous functions whenever you fix n and as x varies in r. And then we're just summing it up against some fixed values. Of course, it's an infinite sum, so that may not happen, or you may not expect it to be continuous a priori. But it turns out that this Fourier support condition implies that f is actually smooth. It's C infinity. Okay. So one, f is C infinity. And this follows from the usual integration by parts argument. No, sorry, that's not what I meant. This is a standard thing in Fourier analysis, right? If you have a very strong decay of your, if you have decay of your function, then you have regularity of its Fourier transform, and vice versa. If you have regularity of your function, that converts into decay of the Fourier transform. Now, decay of your Fourier transform here is being replaced by compactly supported, which is sort of the strongest decay one could have, other than just being the zero function. And that converts into having as much smoothness as you could possibly have, which is being C infinity in this case. Okay, yeah. So Robert says that maybe integration my comment about integration by parts was possibly not wrong. I think you can, certainly one part of the argument I just said, this duality between regularity and localization or decay and infinity, does use integration by parts. And presumably by duality, you can just, the other part does as well. But that's not the part I wanted to focus on right now. I actually wanted to focus on proving this formula, right? So in particular, since it's C infinity, the values at all the integers and every other point is well defined, okay? This implies F restricted to Z is well defined. Oops. And it's well defined at every point, as I said as well. Right. Okay. So with that in hand, let's now think about, I'm going to switch perspectives here, and I'm going to think about the Fourier transform of F. Right. So this is equal to 0 if C is greater than a half. Oops, just greater than a half. And I can actually think about this as a function on the fundamental domain for the torus. Okay, that's a very strange thing to do, but it actually turns out to be quite useful. So from this perspective, thinking about this as a function on the torus for now, or on the fundamental domain for the torus, you know that F as such, F, well, the Fourier transform would then have a Fourier series. Say A of n. Okay, so that I'm saying that the periodization of F tilde is as follows. So I have this for all C from a minus half to a half. Okay, let's say inside. And now the Fourier transform is unique, assuming that the ANs converge nicely. Let's say absolutely summable. Let's just assume that for now. And that actually must mean that it's equal to the Fourier. It must mean that AN is actually equal to Fn. So this is summing over n inside the integers. Okay. So what we really have is actually that the Fourier transform, the real variable Fourier transform, inside the interval of C between minus a half and a half. Well, let me write that better. Is equal to the sum of Fn of ENC as I sum over all the integer points. But of course, this I should also localize. All right, that's not terribly useful. Sorry, it's not unuseful. That's not what I'm looking for at the moment, right? I want a formula for the function itself, not its Fourier transform. Okay. But I do know this for the time being. And so what are we going to do? Well, we're just going to apply the inverse Fourier transform and see what happens. Okay, so yes, now I have that f of x is equal to the integral over r of the Fourier transform, this representation for the Fourier transform, which with respect, oh, sorry. So that's e of minus c dot x dc. And I plug in my representation up here. And that's the integral over r of the sum over fn, e of n c, and there's integers, times 1 from minus a half to a half, xc, and times the character to give us the inverse Fourier transform. Now apply Fubini's theorem and just assume we can do so for now. All right. We'll justify in a moment why we can. So I apply Fubini's theorem. This is going to give me the sum over n in z of fn, looking good so far, times an integral, okay, of what though? Of minus 1/2 to 1/2 of c, and then e of c times n minus x dc. And I can actually rewrite that integral as just minus 1/2 to 1/2 of this character. And by definition, that actually is equal to, or not by definition, sorry. It's a classical computation, one that one sees in a Fourier analysis course, that this is actually equal to sine of pi x minus n over pi of x minus n. So that altogether, this is just the sum of fn times this expression, which is what I claimed. Okay, so why we sort of ignored issues of convergence so that we could so that I could justify switching orders of integration and so on. So I would like to know that the sum of fn is absolutely summable and this sort of thing, because this expression right here is always less than or equal to 1. And why is that the case? Actually, maybe it's not the case. So I'll just assume that as another condition. And let's say, no, I don't need that condition, so I should figure out why.
Sorry, are you having trouble figuring out why sine pi x minus n over pi x minus n is less than or equal to 1?
No. I want to know that in order to justify the order of integration, thank you for the question. I want to know that the sum of the absolute value of fn is finite. I think I should have started with a function that wasn't L1 to begin with, which I don't think I said. And that is well defined. Do I have some decay? Yes, yeah. Okay. There is, yeah, we'll see why the fn is summable in a minute. That's going to come up in the next parts. Let's just take it for granted for the time being, but we will see it very soon, I promise. Sorry, did you have a comment, Rob, or someone else?
I'm just not sure f in L1 is quite enough, but
it will be. We'll see why it will be in a moment.
Okay.
Mostly because, okay, so if there are any other questions aside from potential issues of convergence? I guess not. So why are we going to get to, how are we going to get around that? Sorry, the issue of convergence that I glossed over just a few minutes ago, or just a half a minute ago even. It's going to be contained in what I'm going to call the Polya Plancherel sampling theorem. Okay. Now for this, the setup is very similar to before. I'm going to have a function defined on the real numbers whose Fourier transform is subordinated once again in the interval from -1/2 to 1/2. Right. Before I sort of justified why it's a smooth function and its integers and its value on the integers are well defined. But now the thing I want to go over is that the LP norms are comparable. Which LP norms? I mean, if I look at the function on Z and I calculate its little LP norm as a sequence, that is comparable to the big LP norm as a function on R. Okay. A priori, this wouldn't make any sense. If you took any, if you just took a generic function f in LP for some fixed p, say p equals 1. So you take a generic integrable function, Lebesgue integrable function, is not defined. It's only defined up to sets of measures 0, right? Of which the integers are they're a set of measures 0 for sure, as are the rational numbers, which is much bigger and dense even. So this isn't something that's true for every LP function. This is something that's true when you have something like this very strong condition on the Fourier support. All right. And now taking p equals to 1, well, that is saying, so this inequality, right? Recall just this means that f and LP of z is less than or equal to some constant times little f in big LP of R. This constant c doesn't depend on the function at all. It depends on p, sure. But also I have the reverse inequality for some other constant c prime. I have the reverse inequality, okay? And these constants, again, are allowed to depend on p, but they do not depend on the function. Okay. So let's go over how to do this. It's actually pretty nice, but by no means obvious. So let's start by let's start by fooling around a little bit and just trying to see how one might do such a thing. Okay, I really want to be able to compare the first idea that one has in sort of doing this sort of thing is saying that f of, sorry, use a different color. No, crap. Okay, I guess I'm not able to. Oh, here I am. Sorry. So what I was saying, the first idea one would really like to use is saying something like, okay, if I'm expecting these sums to be comparable, then maybe the points are comparable, nearby points are comparable. So I want to say something like f of n is roughly f of x for all x close to n. Say x minus n is at most 1/2. Okay, so you sort of round your real point x to the nearest integer. Okay, and then if I could do this in a very precise sense, then I would just like how Riemann integrals are, I use Riemann integrals to approximate real integrals or actual integrals, sorry, Lebesgue integrals. Then you just sort of assume there's some kind of approximation argument that allows you to convert these sorts of sums into actual integrals, right? Okay, that seems like a very reasonable maneuver to make. And this is sort of true, but not really. This Polya Plancherel theorem is kind of a manifestation of that idea. But really what's going on in the background is something called the uncertainty principle, which is telling you that since my function has Fourier support inside this interval from -1/2 to 1/2, it's essentially constant on intervals of length 1. Okay, so let me write that down. So the support of F hat being contained in here implies morally F is essentially constant. On intervals of length 1. This is the uncertainty principle. Or one form of it. Right, and so this matches very closely with our idea that f of x is roughly f of n, where n is the nearest integer to x. Okay. But fooling around a bit, this is actually quite, you can't prove anything such as there's nothing exists like this, like say f of x is less than or equal to 10 f of n, or greater than or equal to f of n over 10. There's nothing comparable like that you can do. So instead, you kind of have to think about how you can use this a little more deeply. And the cool trick is to use a reproducing formula, which we've seen before. We saw this coming up in when we sort of threw in some Littlewood Paley theory to prove the boundedness of the Euclidean spherical maximal function, right? So let's do that again. We know that if I take some function, let phi be between 0 and 1, okay, a smooth function, C infinity even. Let's write this better. Of the real numbers, so C infinity of R, with 0, phi always between 0 and 1. And I'm going to take phi equal to 1 on -1/2 to 1/2. And I'm going to assume the support of phi is contained in -1 to 1. Okay. Then when I look at the Fourier transform of F at a point C, that's actually equal to Fourier transform of C times phi of C, right? Because I assumed that the Fourier transform of F was supported in -1/2 to 1/2 already. And I just multiply it by something that is 1 on it. And then when the Fourier transform is 0, I'm multiplying it by something that is possibly non-zero, but for outside of some window is definitely 0 anyway, in any case. So Fourier transform, or the inverse Fourier transform as well, converts multiplication into convolution, which just means that F is going to equal F convolved with the inverse Fourier transform of phi, which I'm also denoting by twiddle. It's a small technicality that is actually the inverse Fourier transform rather than the Fourier transform. But that's not really important for us at all. Great. So what can we do now? Well, we can write f of x. We write out this convolution. So this is actually equal to the integral of over r of f of y times the Fourier transform of phi at x minus y dy, right? Okay, great. Now applying the triangle inequality, I can show you, well, we have that at a point n is less than or equal to the integral over r f of x times phi tilde of n minus y. Oops, sorry, that's f of y dy. Sorry, why is that? I just wrote out what where the convolution was, and now I've applied the triangle inequality to take this absolute value on the outside, throw it in on the inside, possibly losing a lot of cancellation. Okay, but what do we see from here? Well, we see that if I take the sup over all n, right, in that are natural numbers, then that's less than or equal to the sup of this over all n. And well, I can just apply Young's inequality to say that this sup over n is at most, well, it's the sup over every point y in R of f of the absolute value of f at y times the integral phi n of y. Sorry, phi, the Fourier transform of phi at n minus y. And that's an integral over R. Right? Now, this term does not depend at all on n, and that's actually just equal to the Fourier, the L infinity norm of f on R. And the sup goes over here, and that is something that is, well, I just do a change of variables, and this thing is always constant. It's equal to some constant. Why is that? I have that phi is C infinity and compactly supported, so it's Schwartz. And you know, this is just the integral of a Schwartz function, because the Fourier transform of a Schwartz function is also Schwartz, and the integral is therefore finite. And that integral doesn't depend on n anymore. So in particular, we have that this is always less than or equal to the L infinity norm of f over R times the integral, oh, I can put it this way, sorry. The L1 norm of the Fourier transform of phi on R. Great. So I actually have proved this when p is equal to infinity. I've proved, sorry, I should have said, let's start with proving, we'll start with proving this inequality. We'll show that when you sample on the integers and take the little LP norm of this function, it's going to be bounded by the LP norm of the original big function, of the original function on R. Okay, so we've shown that happens when p is equal to infinity. And you might ask yourself, well, why didn't I just do the following? Why didn't I just say that the supremum over n and z of f of n is at most the supremum over a bigger set, right? Sup over x in z, x in R of f of x. And that's because this little L infinity, this big L infinity norm on R is actually an essential supremum. So it's only defined up to sets of measures 0 again. And this argument allows me to circumvent that technical obstruction, right? I can go back and I can describe why, since f is compactly supported, it has, its Fourier transform is compactly supported, it makes sense at every integer, and then I can say the essential supremum has to be an actual supremum and so on. Or I can actually just use this nice short proof that avoids the kind of the annoying facets of LP spaces, or at least LP spaces on R. In the sense that the annoying part is, you know, like an LP function isn't really a function; it's just an equivalence class of functions. This bypasses that nicely. So that's why I didn't do it like that. But let's go on into p equals 1 now. So that was p equals 1. Or sorry, that just before was p equals infinity. So p equals 1, for which I want to show the L1 norm, little L1 norm of f sampled on z is at most some constant times the little L1 norm of the function on all of R. Sorry, the big L1 norm. Great. So this, so what are these sides actually meaning? This is a sum over sum over f of n, and this is the sum over. Sorry, this is the integral. I want to show this integral over f on R. So here's where I'm actually going to use the fact that f is equal to f convolved with phi tilde, right? F equals f convolved with the Fourier transform of phi. And what I get to do is I get to say that this is equivalent to this inequality on little L1 and big L1 of R. Just because both of those are equal to f. Okay. And now at this stage, you sort of just like to apply Fubini's inequality, essentially. Right, sorry, Fubini's theorem and Young's inequality. Right, so how does that go? Yes, let's just write out what the sum is. So the sum over f of n is equal to the sum over f convolved with phi tilde of n. And that itself is equal to the sum over the absolute value of an integral, f of y phi tilde of n minus y dy. And I use a triangle inequality to move that absolute value inside. Right? Cool. And now you just, sorry, this is the sum over n. That's an integral over R. And now you take the soup over this on the outside, right? So sorry, I apply Fubini's theorem here. That's the integral over R, sum over n of this. That sum over n, I get to pull f of y out because it doesn't depend on n at all. So I just have a sum over the Fourier transform of phi at a bunch of points. And this is all integrated with respect to y. And now this is of course less than or equal to the soup over y of the sum. Times the L1 norm of f. Great. Okay, and yeah, so this happens to be bounded, of course, again, because phi tilde is Schwartz. And so I can sum up a whole bunch of points, and then this is now one periodic function, and that's on a compact space. It's got an absolute maximum. And so this is just some constant that depends on phi. And this is, again, the L1 norm on R of f, of course. So we have the same statement when p is equal to 1. Great. Now we want p between 1 and infinity. All right. So let's take p between 1 and infinity. How would you do this? So you kind of like to emulate the previous one. And well, okay, actually no. Maybe as a first step, you might think, I have a bound at 1, at p equals 1 and p equals infinity, why don't I just interpolate to get a bound in between? Unfortunately, interpolation is not applicable here, at least not in any of the forms that we've seen so far, because the spaces aren't set up correctly. So interpolation, question mark, an absolute no in this case, because what am I going to do? I'm going to start with some function f on R to the complex numbers, and I'm going to introduce some restriction operator, say R, that just takes f and is defined as f restricted to z, which is clearly a function from z to c. Well, our interpolation spaces are things on L1, or sorry, our interpolation spaces require an LP to an LQ, and we get everything in between. But this is not a well-defined operation on all of LP. It's for this very special subspace as Fourier transform, supported in -1/2 to 1/2. This Paley-Wiener space, as it's called. Okay, so we don't get to apply interpolation. That's fine. Let's try going back above and using Young's inequality a bit more. We try and do this. So how would we try and do that? I'd say that, so what's Young's inequality? It is for P, Q, and R between 1 and infinity, with 1 over R plus 1 equal to 1 over P plus 1 over Q. It's the inequality that F convolved with G on LR is at most the LP norm of F times the LQ norm of G. And now when we look above, the unfortunate thing is the LR norm is not the same as the convolution norm. We don't just get to do that. So we don't actually get to apply this either, not straight away at least. Right, so the space that this convolution is over, it's not matching this one, because one is going to be continuous and the other one's discrete, at least naively. Okay, still we have some hope, and here is actually a really clever idea that comes into play. I said before that trying to prove something like f of n is at most 10 f of x, where n is the integer, that x rounds to, that's going to fail. But we can do something else. We can define a function psi of x as the sup over, two sups actually. No, one sup. Sup over u in -1/2 to 1/2 phi tilde of x minus u in absolute value. So this function isn't, it doesn't have the regularity that phi tilde does anymore, but it has the decay that phi tilde does. Since phi is Schwartz, it's Fourier transform, phi tilde is Schwartz, and also the absolute value has all the decay that you want. The absolute value is generally not going to make a Schwartz function Schwartz anymore. But then also the supremum preserves the decay as well. And so this function psi of x decays as nicely as you want at infinity, right? In particular, up to, this is like 1 plus x to the minus n. All right. Now we can use this. And this is the clever part of the argument. So I already know that psi, so let's just look at this for a moment and compare it to psi tilde. We know that psi of x is actually greater than or equal to psi tilde of x, right? But it's actually greater than or equal to it in the whole interval, right? Because it's the supremum over all of it. And so let's write that as psi of z. Let's make that cleaner. Psi of z, where x minus z is at most a half. Okay. So how can I use this? Well, I'm going to go back and I'll write f of n as f convolved with phi tilde again at n, right? And that we know is by convolution at most, what was it? F of y in absolute value times the Fourier transform at phi at n minus y. This is with respect to y, integrated with respect to y. But this turns out to be at most the integral of f of y phi tilde, not phi tilde, sorry. Psi of x minus y ty. And psi is, oh, I don't know why I put absolute values there. I didn't need it. Psi is always non-negative, right? So this is a non-negative kernel inside of here. Great. And okay, we see that at every point. So then I can just take the absolute value of f of n. Sorry, this should have been absolute values here. And I take that to the pth power. Right? And sorry. I want to write this as f convolved with psi at x to the pth power. Oh, the absolute value of f. And we can actually integrate this over minus a half to a half. So because this applies to every x such that x minus n is at most a half, right? So I do that, do the integral from minus a half to a half of f of n to the p. Well, on the one hand, this is just f of n to the p, but on the other hand, it's at most the integral from minus a half to a half of this expression. Oh, yeah, dx. And I need to be a bit precise here. I actually want to say the following. That's x minus n is close to or close to each other, right? So this is actually, say, n plus u, where u is between minus a half and a half with respect to u. And now you sum up over all the n's. And this is just the integral over r now. Oh, sorry, this is to the pth power. Right? And here I can finally apply Young's inequality. Right? So I know that the LP norm, the little LP norm of f is at most the less than or equal to the LP norm of f convolved, or the absolute value of f convolved with psi, the big LP norm. And Young's inequality, I will just take Q is equal to P. So Q equals P and R is equal to 1. So that means that this is less than or equal to F in LP of R. times psi in L1 of R. And again, phi was Schwartz, so psi has arbitrary decay as it goes to infinity, and it's definitely an L1. Great. Are there any questions about how to get P between 1 and infinity? At this stage, what I've shown is so far for 1 less than or equal to P and infinity, we have F in little LP of Z is at most F in LP of R. Okay. Are there any questions on that so far? Okay. Now we're going to prove the opposite inequality. And that is actually a little bit easier, it turns out. So for this, we will use the Nyquist Shannon reconstruction formula, or the sampling theorem from before. So in particular, let's say f of x, or we're going to use a slight variation of it. Instead, we're going to take f of x is equal to sum over f of n phi tilde of x minus n. Okay, n in z. Yeah, this is proved just like the way, just like the Nyquist Shannon formula was proved. And note that that issue of convergence, I don't have to worry about now, because I proved the right bound that I needed there, which was this inequality right here. I needed that one. I don't need the one I'm about to prove in the Shannon-Nyquist formula. And so it's not some circular logic that's going wrong here. Okay. All right, great. So I've got those for my points. And okay, let's do p equals 1 and p equals infinity again, just like before. Okay. So for p equals infinity, I just take absolute values. Right? And then I apply the triangle inequality to get that. And this is just less than or equal to the soup over f of n over all the integers times the sum over this over all the integers. And we've seen that that's a finite constant. Once again, that depends only on phi. All right, so that gives us p equals infinity. Now let's do p equals 1. Which means I want to sum this up over, oh no, I want to integrate this, I'm sorry. Integrate over x. And so I'm going to have this sort of integral. And, well, yeah, with respect to x. And now I just have the reverse, right? I estimate it differently like I did before. And this is going to be a sum over fn over n times z, that's absolute value, the integral over phi tilde of x minus n dx, an absolute value here. This is again some finite constant. It doesn't depend on n. And what we're left is the L1 norm of f on z, the little L1 norm. So now I have the bound for okay, so we have at this stage f on L1 of R is at most some constant times the little L1 norm of f. And similarly at infinity. And once again, you would like to say, can I just interpolate and save myself any actual work? Oops, that's an L infinity. Little L infinity. And it turns out you actually can do it now. You can actually interpolate. And that's because you're starting with functions that are honestly well-defined, right? You're starting with sequences and you're ending up with LP bound on an extension of those sequences. And so we define an extension operator, E of F, at a point X by just the Shannon-Nyquist formula that we had before, sum over Fn, X minus N over all N and Z. And this does take functions, right? So F goes from Z to C, then that gives, E of F gives a function that goes from R to C. And we do have the correct L1 and L infinity bounds for it. We're happy to have our target space be a subspace of it, right? Like the fact that the extension operators have Fourier transform localized is not a problem when we end up in that space. It's a problem if we started there and tried to claim a thing for all of LP. But we're not doing that now. And so you can just apply real interpolation and get that you have LP boundedness. Great. So are there any questions on the proof of that? There's a little muddling around at the beginning because I wanted to actually show that this is not at all an obvious thing. It has a very slick and clever proof, but I wanted to make it clear that it is actually clever. Okay, I'll assume we're cool there. So I'm going to mention another theorem due to Bourgain, or a lemma really, I should say. He used it in his work on arithmetic maximal theorem and ergodic theorems. Yes.
Sorry to do this, but would it be okay if we took like a 5-minute break?
Sure. Yeah. Sorry, I'm just chugging along. Let us pause the recording. Great. Okay. Back from the short break. So the next sampling theorem I want to talk about is one from Bourgain's work on ergodic theorems for arithmetic sequences or subsets. So this is this we'll see is a prototype of the Magyar Stein Wainger theorem, and he doesn't ever. No, he does actually. Sorry, he does state this somewhat precisely as a lemma in one of his papers, but maybe not the first one or two. So what's the setup here? We're going to start with some kernel. That's going to be an L1 function in R. And then we're going to consider all the isotropic dilates of that kernel in order to form a maximal function from it, just as we've done in the past. Right? And we'll assume that that maximal function has a maximal function inequality on some LP space for p less than or equal to infinity. Sorry, yeah, but not including 1, right? We've seen that for the maximal functions we care about, such as the Hardy-Little maximal functions, they're never bounded on L1, but they're bounded on all LP for p bigger than 1. And so we'll ignore 1, though you'll see the arguments could go through for p equals 1 if such a maximal function were ever bounded on L1. But none of the interesting ones are. Right, okay, so that's how I have, I've formed a family of kernels. Remember, alternately, you can define k of t so that by the Fourier transform, so at a point C, it's just k, the Fourier transform of k at t, c. That was another way to define the isotropic dilations that we wanted. And now we're going to define a whole family of kernels that depend on some modulus q. So we pick a modulus q, that's a natural number, and kq of t, which is going to be defined for all t greater than 1, or sorry, for all t greater than 0, this kernel. So it's defined on the Fourier transform side. When q is equal to 1, let's just pretend q equals 1 for a moment. We have k1 of t of x is the integral, by definition, the integral over r of this. Oh, well, yeah, I'll leave it like that. Then psi of c e to the minus x c dc. So this is the dilation that we're wanting, right? The isotropic dilation. But now it's localized by this psi function right here. And so the Fourier transform is localized by psi, right? So what is psi? Oh, psi should have been phi. Oh, let's just change phi to psi now. So it's some Schwartz function that is, say, supported in the interval from -1/8 to 1/8. And if you want, you could also assume that its psi is equal to 1 on -1/16 to 1/16. This is a bit smaller than before for some natural regions that'll come up a bit later on. But the point is, this H is O of 1. It's not like getting smaller as Q is getting smaller. Okay. So K1 of X, it looks like this kernel. It has a Fourier transform that is just this expression here that's underlined now. And you can involve with, so that's because psi has this localizing property, right? We know that it's well defined on the integers. And so KQ of T is well defined on Z, and you can form convolution with it on Z. Okay. And what Bourgain shows is that, all right, you can define these for a whole bunch of Qs, for any modulus Q. It's bigger than 1 as well. And if you start with just some maximal function inequality on LP, then by only conceding a factor of, say, 4, you get that this is at most, you get that these new maximal functions that depend on Q are also bounded on LP, but this is little LP of Z. I should have drawn little LPs, sorry. Okay. And so that's pretty cool. I mean, we started out with one maximal function on R, and we've now shown a whole family of maximal functions on Z are bounded as well. Let's think about why this would work for just Q equals 1 for a moment. Okay. And that's going to be, that actually relates to our previous discussion. So let's go back up to it and discuss it a little bit. So in the course of doing all of these, showing these LP norms are comparable, these discrete ones and these continuous ones for a certain class of functions, we could have introduced LP norms that are taking values in, we could have introduced functions that take values in Banach spaces and LP norms that take that into account. So in particular, let's get a different color going on here. Okay, we could have said F maps, say, R to some Banach space B. Assume B is finite dimensional, something like L infinity of N. I don't think that's visible by Bourgain actually takes L infinity of the natural numbers, which is fine. Okay. So now I can talk about, well, if I look at a point F, evaluated X was some real number, and suppose that this is now my Banach space norm, this norm. Okay, so this is something, so F of X was inside my Banach space, and now this is some real number. Well, non-negative real number because it's a norm on a Banach space. Great. Okay, and I can go through and I can actually talk about, well, if I take the sum over F of N under this Banach space norm to the pth power, and the 1 over pth, that is an LP norm of F, and that should be LP of R to B, right? I start with a function on R and I end up with a function on the Banach space. Then I'm measuring the LP norm with respect to that. And similarly, you could also imagine that the integral works as well. This is the LP norm. The big LP norm, sorry, This is the little LP norm of Z. I should have, I'm sorry about that. That is of Z, little LP. This is the big LP norm of R to B. Okay, and then it turns out that these norms are also comparable. And all you have to do is go back through the proof and just start writing down those apps. Every time I do an absolute value, I'm just gonna put in the norm on the Banach space. And then things like Holder's inequality or Young's inequality are all fine. Oh, there should have been absolute values there in the first place. Now norms, and so on. And you just repeat that whole argument, replacing all of the absolute values by Banach space norms, and doing the summability or integration as you need, the sum or the integral as you need, and you conclude that you get this theorem. Sorry, you conclude what? You can conclude, what can I say? You can conclude that the little LP of Z to B norm is comparable to the big LP of Z, no, sorry, of R. To B norm. Oops. With that, it's just a change of notation. This is an incredibly useful trick in harmonic analysis. It's how you can extend Kohler and Zygmunt theory to prove things like Littlewood-Paley theory sort of almost immediately. And by instead of taking the Banach space to be L infinity, you take it to be a little L2 on Z. And you can get a whole bunch of other like vector valued and assorted inequalities in harmonic analysis by this sort of trick. Once you've proven a theorem that's genuinely strong enough or robust enough to replacing these absolute values by Banach space norms. And the reason why I assume the finite dimensionality is just to make any of the definability issues just disappear. Okay, and once again, we'll be able to take a limit of finite dimensional Banach spaces to conclude what we want by monotone convergence. Great. So that is actually how you could get Q equals 1. Why do you get Q equals 1? It's because I can move the psi onto the F, right? So if I take So I have my average or my kernel, just to recall, is this Fourier transform of K times C, psi of C, E of X minus XC, dXC, okay, over R. So as a Fourier transform, this is just, oops, no integral here, KT of C, psi of C. And, so if I look at this convolved with my function, well, then the Fourier transform is just KT1 of C times F hat of C. And we can squeeze in some other function. This is also equal to this times psi of C over 2. Because this will be 1 when you need it to be and 0 otherwise. And so I can just throw that on as KT1 of C, psi of C. And then times psi of C over 2, Fourier transform. Oops. And this is localized. So psi was supported on -1/8 to 1/8. So psi over 2, or you know, the domain is half now, is supported in -1/4 to 1/4. And so that has support inside of -1/2 to -1/2 to 1/2, or we're well insulated there. And we we get this comparison. We get that F hat has the form that we had wanted for applying the Shannon-Nyquist, not the Shannon-Nyquist, sorry, the Polya Plancherel sampling. Okay. By taking B to be this L infinity space. Great. Now, the real work in doing this is actually getting all the larger moduli Q. Okay, I won't go into the details of Bourgain's theorem, though I accidentally allowed myself a lot of room for that. I want to do the Magyar, Stein, Wainger theorem. Proof of Magyar, Stein, Wainger. Their transference / sampling. Yes. So I should back up and just scroll up to what it was for a moment so everyone can recall. It's basically the same thing as Bourgain's, but very nicely generalized. So what was our transference lemma again? I get this multiplier, which I'm calling mu, and I periodize. It's localized to a box of width like 1/q, or half of that. Sort of standard axis parallel box centered at the origin, and then I periodize it to make it a function modulo 1, a periodic function, and you can define an operator based on that, the Fourier multiplier based on that, and then we have these comparison of these LP norms. Okay, so let's remember that. Okay. Just pulling up my notes. Okay. So again, well, proof. Let's just restate the lemma real quick. Maybe lemma. Right. B1 and B2 are finite dimensional vector spaces. Banach spaces, sorry. And Q isn't a modulus. We define, we have some multiplier, mu, which goes from -1/4q to 1/4q in every direction. It takes values that are linear maps between our Banach spaces B1 and B2. Okay. And yeah, that's great. Yeah, so how do we use this? So that's going to be, say, yeah, okay. So I want to say now MQ at a point C is going to be the sum where I just periodized this. So M of C minus M/Q, I sum over all ZD points M. So this is a higher dimensional version of the theorem the lemma we just saw by Bourgain. We didn't fully prove. And I'm going to use as part of it a higher dimensional version of the Polya Plancherel theorem / the Shannon-Nyquist ones, which I'll leave to the reader. You sort of can just do everything. It extends to higher dimensions pretty readily. And unfortunately, all the constants that arise in those inequalities, at least the way I did it, can depend on the dimension. But it's harmless. It grows like something like 5 to the d or some constant to the dimension, where that constant is a actual universal constant. Yeah. Right. Okay. So this MQ is now a map. Sorry. It takes at each point C, inside the torus, inside of R mod Z to the D, it takes as values a linear map between the Banach space B1 to the Banach space B2. And so when we define this operator TQ, I'll call it TQ of ZD, in fact, on a point F, well, that'll be defined by Fourier multiplication. So this is going to equal, well, again, just by multiplication, that. So what is F actually? F here, where is it living? Where is it taking values into? It's going to map from ZD, so F goes from ZD to B1, right? And then this multiplier will take the values in B1, map them into B2. Great, okay. And what do I want to show? I want to show that LP of ZD to be, no, oh yeah, this. It's a bit cumbersome to write out. So I have these Banach space valued functions that, and I'm going to map between LP spaces for those Banach space valued functions, right? Where this T of RD is something that I haven't given you yet. What is it going to be? Well, it's defined as just it's defined also by Fourier multiplication. So for a function f on RD, taking values inside the first Banach space, the real variable Fourier transform at a point, I'll also call it C, it's maybe not so great, is defined as mu, no, just mu, times the Fourier transform of f at C. Oh, this is xc. Okay. All right, that's a bit to digest and to process. But let's again, this is really a good generalization, a really useful setup when we take B1 and B2 to be L infinity. Okay, little L infinity. Right, okay, so how am I going to prove this? Well, I can write out these things, I can write out the kernels for these maps if I wanted. And how, that's actually a good thing to do. Okay, why? So T, the kernel for, so like K of RD be the kernel for, oops, T of RD, right? So as such, this means that K of RD at a point X is going to be the integral of, well, mu of C, the inverse Fourier transform of mu, right? And so that's on RD, and that is with respect to C, which are d-dimensional vectors. This is X. So that's an inner product there. Okay. Similarly, KQ of ZD of X would be the integral over TD of M of Q, XC, e to the minus XC dx. Right, and that is actually a little bit different now. It's the sum, it's the integral over the sum of this periodized version of mu. So mu of c minus b over q. This is all the b in z mod q to the d, and e of minus x dot c. Okay, and you can Fibonacci, and you can sort of, you can switch these two, right? You kind of get a relation, see that these two are not too dissimilar. Okay, but they are not the same, and we're going to see how that means. Okay, so since q is greater than or equal to 1, and mu was supported inside minus 1 over 4q to 1 over 4q in every direction, mu is, we have that this kernel is smooth, and its values at every point x is well defined, including x being the integers, right? And so we're going to use that to say, we'll define k of zd, oh, yeah, just k of zd, no superscript on q here, right, is just going to be k of rd restricted to zd. Great. And then this allows us to define an operator, which I'll call t of zd. Again, no superscript here, no q, where it is defined, yeah, it's just defined as convolution. K of zd, convolution on zd with f, also defined on zd. Okay, phew, lots of moving parts going on. Well, let's see how they interrelate. So the main thing, sorry, were there any questions so far? I've just thrown a bunch of notation at the moment, so hopefully it's not any questions, but understandably if there were. So I'll say before, what we've shown is the following. The Polya Plancherel stuff.
Sorry, Kevin, could we go back to the previous slide? I just want to make sure I understand something. I think you might have even said this, but I just forgot. So
Absolutely.
in that integral defining KRD of X, for example.
Sure.
So is the idea here that if you were to plug in an element of your Banach space B1, because I assume KRD is a linear map from B1 to B2.
KRD is a yes. Yeah.
So
why is that? Well, this is just modulating a bunch of linear maps here that you integrate over.
So this integral, if you were to apply this this operator KRD of X to an element of B1, the way this acts is you apply this modulation and mu to that element of B1, and then you evaluate the integral.
Yep.
Okay.
Exactly.
Yeah, just wanted to make sure.
Yeah. So this character is kind of, the mu is going to spit out a map at each point. This character will rotate it, but mu is doing this in a smooth manner, and the character is smooth, so it's not doing anything too crazy. And then the integral is going to tabulate all of those. And the integral, I mean, you can define the integral sort of in a standard way as say, you know, these Riemann sums and taking the limits and stuff if phi is smooth, or sorry, if mu is smooth. Yeah, it is a little bit to get one's head around at the beginning. Yeah, I admit, and I won't go into maybe every technical detail about this, just sort of due to time. You know, like I have no, I'm not going to recover all of Banach space theory and the ins and outs of that. There's lots of, there are lots of things to be wary of. in this. And if you're worried about it, just always assume conditions that'll get you to it. And at the end, there will be some limiting argument that you can do to get rid of those conditions. Yeah, sorry. Okay, so with that in mind, I'm going to say that the Polya Plancherel told us that the following was true. It told us that how did I end up with blue? It told us that if I had this of RD, nope. Now this is going from LP of ZD to B1. It's a most sum constant by the same operator norm, but on RD. That's what we ran through before. Okay, so we have that already at our disposal. And also we know that we have any sort of, when we take a function f on the torus, so this is Nyquist Shannon now. Taking f with the Fourier support, this is the higher dimensional versions that I alluded to previously. Then we know also, well, yeah, this plus PP, Polya Plancherel. We know that f in L, little LP of CT to B1. Oh, sorry. There's a map to LP of ZD to B2 is bounded by the same thing, but on R. Ooh, okay. Just writing out what we already know is a bit exhausting. And so the real question now is to how are we going to leverage this information, right? How are we going to use that to say something about these TQ operators? Okay. And that is actually pretty clever. So one moment. Sorry, just looking at my notes. Right, okay. So where is it? Oh, that ignore question still proof. Ongoing. So if I look at this TQ of ZD, right, then I can use this to similarly define a TQ of RD, which is defined very much like how T of ZD defines T of RD. Right, I pick a fundamental domain, I assume I'm localized there, that gives me a function. That gives me the right defined operator. So I guess to be precise, this would be the sum. So the Fourier transform of this as a multiplier would be the sum of B in, let's say, equals minus Q over 2 to Q over 2 rounded down in every direction. and then the integral of mu of c minus b over q. What's here? Oh yeah, that. Oh no, that's not the. Yeah, that's just the multiplier. Sorry, the multiplier is that's the Fourier transform, and all of this times, say 1 of minus a half to a half to the d in every direction. Right. Yes. Okay. So that's how you can define a multiplier, and then the convolution with the inverse Fourier transform is how you can define the operator, right? Or just define it by Fourier multiplication. Yes. Okay. So it turns out you can just do scaling to show that RD here. TQ of RD on LP of RD to B1 into LP of RD into B2 is actually equal to just T of RD. Okay. I should say, yeah. And the same things, the LP RD to B1. Okay, that's a change of variables that allows you to do this. That's good. That was because the original one, this original T of RD had just this centered at the origin. Remember, mu itself was supported, sorry, and minus 1 over 4q to 4q, 1 over 4q. Okay, that's good for us. And now I have two different things to worry about. I have TQ of ZD and a different operator, which is, so this corresponds to, let me write it differently. I have KQ of ZD, okay, as one kernel. And there's a different kernel, which is actually defined as Q to the D times K of ZD at M. So at M, point M, where, so this is if M is in Q of Z to the D, and 0 otherwise. Okay. And the point being that when we are going to extend, right, there's going to be two ways I could extend my function. And one will end up using this kernel, and the other one will end up using this variant of it. Okay. So where does this come from? Well, this one actually comes from, that's this one up here. Okay. And, yeah, sorry. So bear with me for a moment. Oh, I'm going to call this RD. Sorry. No. Okay, ignore what I was just saying for a moment. I have KQ. All right. apologies. This is actually, when you evaluate it, KQ of ZD at a point M. And in comparison to that, we also have the kernel underlying this buddy, right here, KQ of RD. And that is actually equal to Q to the D, oh, K of ZD. Let me check that in a second. Q to the D, K, Q, M of ZD. Yeah, okay. So, well, sorry. The point being, these two kernels are slightly different. Well, not slightly, they're pretty different. Okay. So you do this, you calculate this one, for instance, just by following that change of that dilation in this argument. And this other one comes by just evaluating the multiplier. So how do you do that? Let's say I look at the integral of mu q of z of c e of x dot c minus here dc. Well, that is the sum over b and z mod q. And that's over td, the integral's over td. So then I integrate over td, and I see that I have mu of c minus b over q. You have minus x dot c dc. So I make the change of variables for each of those integrals. It's the sum over b and z mod, that's z mod q to the d, to be more precise. Integral over td, that wraps around, so this is fine. So that's just mu of c e of minus x and then c plus b over q dc. Well, that term comes out to give the sum over b and z mod q to the d e of minus x dot b over q. And the integral of mu of c e of minus x c dc. This last part is, of course, k of zd at x. But this part right here is an orthogonality relation. It's actually q to the d times delta of, well, maybe I should say write it as 1 times 1 of qz to the d at x, right? And so that means that x has to be divisible by q in every coordinate, and that's how we end up getting this claimed thing right here. Okay, and this is not too dissimilar calculation. All right, so there are two different ones floating around, and we need to actually be able to compare them. And then here is the delightful trick that they're able to use. So if you just, yeah, so they say take t, right, sorry, so t this thing here is really only defined on qz to the d. So I'm going to introduce another operator, call it t sharp of q. And that actually maps functions, so operator on functions that say f going from q of z to the d to c. Okay. And that is going to be defined as t sharp q of f at, let's say, q times m is defined to be the sum over n and zd, blah, 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 f of n minus m, oops, sorry, m minus n k zd q qn. Okay. Oh, this is q. Okay. And this actually just acts trivially on a lot of, I write this. You can end up writing T of z d q as T sharp q tensored with the identity on z mod q z to the d, the identity operator. So it just, the way that works is you write every f of x is going to be f of q m plus some remainder r, which is also a vector. And then, so I can make that the r functions, say, q to the d such functions, each indexed by r of f of q to the m, f of q times m, sorry. I apply this operator for each one of those, and then I can sum over all the r's individually. And those aren't affected by this. And what that allows you to do is it allows you to write my LP spaces, LP of ZD to say BI, as it's just LP of QZ to the D to the BI, tensored with LP of Z mod QZ to the D. And that's not a BI here, it's just that. Right, these are just keeping track of these residue classes here. Yeah, and so now when you take norms of T, say TQ ZD from little LP RD, but ZD, ZD to B1, then mapping to LP of ZD to B2, let's draw that this way. Then I know that this is at most the T sharp bound for the same spaces. Times the identity on LP of Z mod QZ. And that has that just has bound 1. So it's at most this right here, which is, that is equal to these spaces right here. And I just said there's a dilation argument that said that that was actually equal to the same thing on T of the D, T of the RD. So you get that and that's an overview of their proof. It's a good exercise to just go through why you can break up this sort of summation right here, right? All I'm saying is nothing deeper than the fact that if I look at the sum over f of n, assume n is just in z, right, for the moment, then, and I look at this in LP, I take the LP norm, this is just equal to the sum over, let's say, r equals 1 to q, and the sum over m in z of f of n, f of qm plus r to the p over 1 over p, all to the 1 over p. right? All I'm saying is I can split it up into these disjoint sets and look at the little LP norm of those disjoint sets. That's all that's saying. And that's nicely encoded as an identity right here. And so all you really have to do is understand this. And that luckily has some dilational structure on RD that you can take advantage of. Right, are there any questions about that? Great, okay, that's where I'll stop for today then.